name's Andre. I'm the educator at the Curtis Museum, and I'm introducing tonight Jeffrey Megivern. He growing up across the river from the Kennedy Space Center. Jeffrey Megivern has found a long found home in space exploration. After working launch operations at the Kennedy Space Center for NASA, Jeffrey moved to California to develop rocket engines at Rocketdyne, and I then moved to JPL to work on the Mars 2020 Perseverance rover mission. He's now an engineering manager over at an organization called Materials Development, Testing, and Failure Investigations. Jeff enjoys video games, board games, music, and tea, and he recently actually launched an Astro Tea company, which is dedicated to raising money for science, technology, engineering, arts, and math, so basically STEAM education initiatives. Really excited to hear about your talk, Jeffrey. Thank you for giving this lecture.
Awesome. Thanks, Andre. No, not a problem. Happy to be here. All right, everyone. So as Andre mentioned, I'm Jeff Megivern. I currently work at the Jet Propulsion Laboratory out in Pasadena, California. I'm going to talk a little bit about the Mars Perseverance mission, which includes the Ingenuity Mars Helicopter. This is all part of the Curtis Museum's lecture series, getting ready for the new vertical lift exhibit. All right, so Mars. In the early days, in the 1960s, we had a series of missions part of the Mariner project. The aim of Mariner was to launch spacecraft to the inner planets. So all of the planets, excluding Earth, that are inbound of the asteroid belt. So that's Mercury, Venus, and Mars. So the picture on the left there is from Mariner 4. It's the very first image up close that we have of Mars. And then next to it on the right, in the 70s, we had a pair of missions, Viking 1 and Viking 2. They both had an orbiting spacecraft that orbited Mars, and each of them had a lander that landed on Mars and took pictures of that landing. The picture on the right is from a composite of images taken during the Viking mission. It's about 174 different pictures that were taken during that mission, and it's still today the highest resolution picture that we have of the entirety of the planet. So anyway, I'd like to kick it off here to give some context for what I'm talking about. We're going to talk a lot about Mars today. So the Mars 2020 mission, or the Perseverance rover, is part of a Mars sample return campaign. So on the left is an overview of what that campaign is. It's essentially, we're collecting samples on Mars now with the Perseverance rover. And then in development, we have another spacecraft that's going to go to Mars, collect those samples, and bring them back to Earth. So we're looking for these 4 scientific objectives over here on the right. We're looking at geology, so understand better what Mars is made of. Astrobiology, so we're looking for signs of ancient or alien life. We're doing sample caching, so this is where we're collecting samples in sample tubes. That's what the video in the middle here is showing, is collecting those samples. And we're doing some amount of preparation for humans, and what that is really, we have a couple experiments. One's called MOXIE, that we're testing different approaches to be able to have crewed missions go to Mars. And so MOXIE is essentially turning the Martian atmosphere into oxygen. And the 2 pictures on the bottom, one is of the shadow of the rover, and the other is of the robotic arm reaching out and collecting a sample. So part of the Mars 2020 mission is this guy. This is the Ingenuity Mars Helicopter. This, of course, is a diagram of all of the parts. It's a relatively simple helicopter. It was the first vertical lift device that we sent to another planet. So it's the first helicopter on Mars. The components are simply blades, which are used to provide lift to the drone. The blades, because the atmosphere of Mars is 1% that of Earth, the blades have to be much bigger, so a bigger surface area to generate the lift, and they spin a lot faster than we have drones and helicopters on Earth. We have antennas, which we use to communicate back to the Mars rover, and we'll also send data to the Mars rover that the rover will send back to Earth. We have solar panels that charge the batteries that are on the Ingenuity helicopter. We have avionics and cameras in this box underneath the rover, or the helicopter. The avionics help determine how to fly, its flight path, help to control landing and takeoff. The cameras and sensors do a couple of things. One, we use them to survey the land. So we will fly, or we were flying Ingenuity ahead to take pictures of the surface to do some analysis of where to collect samples, but also we'll use that to do some tracking. And then these legs let the helicopter land softly, although as I'll talk, we had a final landing that wasn't so soft. And of course, the batteries that power the whole thing. So here's the Mars 2020 team in summer 2019. At its largest, we were about 700 people. This is a team photo, and I'm right there. All right, so Ingenuity. We had planned to fly Ingenuity as something we call a technology demonstration or a tech demo. That tech demo was going to fly 5 times. We're going to take off and land just to prove the concept, prove that we could control a helicopter or drone on another planet, prove that we could collect images during that flight, and give us a sense for what it took to transport this helicopter to Mars and operate it. Well, because those 5 flights were so successful, we ultimately ended up flying 72 times. So that's 72 flights. And instead of just being a tech demo, like I mentioned, we integrated the Ingenuity helicopter into our surface operations. Surface operations are everything that we're doing on the surface of Mars. So we were using Ingenuity to survey ahead. We were using Ingenuity to help us understand the terrain, help us understand potential science targets. This is, of course, the first helicopter on another planet. And instead of the month-long mission that was initially planned for Ingenuity, we flew for more than 2 years. So we vastly extended the life of the Ingenuity helicopter beyond what we had planned. And there's a scale reference down here, and I have a couple photos that show this too. The size of the helicopter is relatively small compared to the rover. The Perseverance rover is about the size of a Volkswagen Bug. And there's a person to give you a sense for the two. All right. So I mentioned Mariner back in the 60s. That's what the Mariner spacecraft looked like. The Mariner spacecraft were just orbiting and flybys. So they didn't have anything that was landing on other planets. They were flying by the other planets and taking pictures and making measurements. The Viking spacecraft had a landed element. So this bulbous object on the right side of the spacecraft is what had inside it the lander that landed on the surface of Mars. And then the other element stayed in orbit around the planet. And then on the right here is an image of the Mars Perseverance rover. So this is the cruise stage. So this is the top of the spacecraft. There is what controlled our trip from Earth to Mars. Then we have the capsule that encapsulated everything. The body with the rocket engines on it is the sky crane. That's what was used to lower the rover to the surface. Then, of course, below that is the rover itself. And on the belly of the rover, that's where the Ingenuity helicopter lived during cruise and landing. After we landed, we deployed that onto the surface. And then this is an aeroshell to help us during entry into the Martian atmosphere. So a couple of the other lecture series lectures in the series have mentioned this, and I thought it was relevant here as well. So back in 1908, we have this John Williams doing this testing of a helicopter here on Earth using one of the engines from Glenn Curtiss. And 110 years later, we have the Ingenuity helicopter being developed. This is the flight model, the version of the helicopter that went to Mars being tested for readiness for installation onto the spacecraft. So some similarities, people pining over their inventions as close as they can get, and breaking our understanding of what we can do as humanity. So we're going to talk a little bit about assembly, test, and launch operations. So assembly, test, and launch operations, or what we call at JPL, ATLO, assembly, test, and launch operations turned into an acronym. ATLO is the phase of the project where all of the components are coming together and to build the spacecraft. And then the spacecraft is integrated with the launch vehicle or the rocket, and then the rocket is launched. So here's another picture of the Mariner spacecraft during its ATLO campaign during the assembly, test, and launch operations phase. This is in a high bay that we still use at JPL. They're just called high bays because they have incredibly high ceilings and some cranes, and they're clean rooms. And on the right here, this is the entire cruise stage. So the cruise element and the rover inside the spacecraft being prepared for some final system tests before we sent it to Florida and integrated it with the launch vehicle in 2019. Here's a video put together by Science News, but the videos are from our project. The first half year, this is a prototype of Ingenuity. Relatively simple. You can see it has legs. There's it's hopping around, can't keep flight for very long. This was early days in the project, trying to understand what it might take to fly a drone on the surface of Mars. And this is Ingenuity. This is the actual spacecraft in a big chamber that's in Martian environment. So this is down at 1% of Earth's atmosphere, or in terms of pressure, that's 7 torr. We have 760 torr here on Earth, and we were doing a flight test. So we were lifting off and landing and making sure that the speeds of the propellers made sense, and that the landing loads weren't too heavy. So after we do that testing and make sure that the spacecraft is integrated with the launch vehicle, we launch. So on the left is the Mariner mission. That's one of the Mariner launches. In the middle is the launch vehicle for the Viking missions. And on the right there, that's the Mars 2020 Perseverance rover launch. I have another shot of that launch. So this is from a camera on the pad during the launch. That's an Atlas V launch vehicle out of Cape Canaveral Air Force Station. Or yeah, Cape Canaveral Air Force Station. They didn't turn into Space Force Station. And here's a longer shot of the Mars 2020 launch at Cape Canaveral. And then it's the 7-month trip to Mars. So once we leave Earth, we get 2 chances to launch to Mars. The 2 chances are we can leave Earth, and then 7 months later, we arrive on the inside of the Martian orbit. Or a couple months later, we can launch, and still about 7 months later, we can arrive on the outside of the Martian orbit. So in 2003, when we launched Spirit and Opportunity, the Mars exploration rovers, we launched them in the same summer. One was launching on the inside of the orbit, and then a couple months later, the other one was launching on the outside of the orbit. That's what enables us to do that. Now, because the Earth and Martian orbits aren't perfectly aligned, we get that chance every 26 months. So every 2 years, they're aligned in a way that we can get there with using the least amount of energy. The rest of the time, Mars is on the opposite side of the sun from us, and it's nearly impossible to get a spacecraft there with any reasonable amount of time or energy. So while the spacecraft is cruising to Mars, it's all buttoned up in a a configuration like this. So where do we land? Before we launch, we make some decisions on where to land. This is an image, a topographic heat map of the Martian surface. And because one of the focuses of the Perseverance rover was looking for signs of life, the astrobiology component, we wanted to look for specific areas of Mars that might have some opportunity to find signs of past life. So here's a shot of the Martian surface spread across a rectangular map. In light gray are all of the JPL Martian landings to date, or up to Perseverance, and then Perseverance is in white. For the United States, JPL is the only organization that's gone to Mars. We in 2020, summer of 2021, when we landed. So we launched in 2020 and we landed in 2021. Sharing the landing year was a Chinese rover, and it was the first time that they landed on Mars, but they made a similar trip as we did. So we look for there were 3 potential landing sites during the planning for Perseverance rover. And what we ended up on is what we call the Jezero crater. So the right side of the screen is the Jezero crater. These rocky outcrops, 2/3 across the screen, are the edge of the crater, or the crater rim. And we have what we could call a river delta, an ancient Martian river that dumps into this ancient Martian lake. So if you can, I'm using some liberties here, calling them rivers and lakes, but the idea is on Earth, when we have a delta, when there's a river or a stream or a constrained body of water dumping into a larger body of water, a lake or an ocean, those deltas on Earth are rich with life. The soils have a lot of components in them that are wriggling around and moving. So the thought is there's no reason that type of life is constrained to Earth. So we targeted a river dumping into a lake, or the Jezero crater, as our landing site. So this ellipse is approximately the landing location. It's an ellipse because we're coming in a given direction as we enter the Martian atmosphere. So we give ourselves a little leeway in the direction that we're landing. And we nailed the landing. We stuck the landing. So I'm going to talk a little bit about that. So here's a graphic of what that landing looks like. Up here in the top left is the cruise stage. We dump the stage that helped us get from Earth to Mars as we enter the atmosphere. And then we reorient ourselves and we enter the Martian atmosphere. Now remember, the Martian atmosphere is 1% that of Earth. So it's not enough to slow us down on its own. When we do this on Earth, we use the Earth's atmosphere to do most of the slowing down. It's something we call aerobraking. And so when we're landing a spacecraft back on Earth, we will use the atmosphere to do a lot of the slowing down. And then we'll deploy a parachute so that we slowly drift to the surface. But we don't have that opportunity on Mars because it is only 1%. So it's not enough to slow us down. So when we deploy the parachute, it's deploying supersonically. We're ripping through the atmosphere, going super fast. But because there is some atmosphere, it's enough to heat us up. So we have what we call a heat shield on the aft end of the spacecraft, taking a lot of heat load. So we're heating up the spacecraft. We deploy this parachute supersonically. Then we look at the ground. We're looking for a final landing location. The The planning that we did to choose where we're going to land has a fair amount of information, but nothing beats having eyes on the landing during the landing. And so we have this system, we called it the terrain relative navigation system or solution system. And what it's doing essentially is looking for topography, looking for rocks, and making the final decision for where the rover is going to land. Then we deploy the sky crane. So we ditch the back shell, which has the parachute on it. We fire up the retro rockets on the sky crane, and we lower the rover to the surface, and then the sky crane flies away and crashes into the ground. We call this landing process 7 minutes of terror. The reason we call it 7 minutes of terror, because it takes about 7 minutes for a communication signal to get to Mars and about 7 minutes for it to come back. What that means is the rover and its spacecraft friends are making all of the decisions about landing. It's looking for terrain all on its own. It's deciding where it's ultimately going to land all on its own. It's understanding that it touched down all on its own. So at JPL, during a big landing event, we hold our breath for 7 minutes and hope that it landed. And then we finally get the beep of confirmation that it landed. And then that's when we cheer. So anyway, the 7 minutes of terror, and I have some images of that. So this is the beginning of the parachute deploying. This is the parachute filling up with the Martian atmosphere, which is carbon dioxide. There's the parachute completely full, and the pattern on the parachute spells something out in a binary. That's the heat shield. So these images of the parachute are a camera looking up from the back shell, and this is a picture of the heat shield. So this is from the rover looking down. This is a picture of the ground during the terrain relative navigation step, looking for a final place to land. This is what we call the top deck of the rover. And remember, the Ingenuity helicopter is on the other side of the rover. So the Ingenuity helicopter is on the bottom of this thing that's getting lowered to the surface. You can actually see it in the little cartoon here. The Ingenuity helicopter is closer to the ground than anything else is at this stage. So then we lower the rover. So the picture on the left is from the sky crane looking down at the rover, and the picture on the right is from the rover looking up at the sky crane. So these rockets in the corners of the sky crane are actively firing and holding the whole thing up. Then you can see the plume of the rocket kicking up dust. This is another picture from the sky crane looking down at the rover. And this is clouded with dust that the rocket engines are popping up. And then we have confirmation. We've landed. Once we sense that, once the rover senses that it's landed, it cuts these lines, and then the sky crane flies away and crashes into the ground. Fun fact, these lines that are lowering the rover are nylon. They're just nylon rope. Now they have a special braid that makes them particularly stiff and suitable for this environment that's low pressure and very cold. But otherwise, it's nylon rope that you can find at the department store. This is a picture from another spacecraft in orbit. And you can see it picked up, this is the parachute on the top here, and the rover below the parachute, it picked up the landing, which is incredible. And here's another picture from the orbiting spacecraft, and that's the rover. That's the rover as landed. The light gray plumes looking things on either side of the rover are from the sky crane. So that's the dust, the Martian regolith that the sky crane blew away from the rover during the landing. And then that's the smoke from the sky crane that flew away and crashed onto the ground far away from the rover. And this is a picture from the rover of the smoke piling up from the sky crane. Again, so there's the 7 minutes of landing on the surface, and before the rover touches down, we deploy the wheels. So the wheels touch the surface before the Ingenuity helicopter does. And then we open up our cameras. So this is the very first picture that we received at JPL from the Perseverance rover. This was the very first time that we understood that our systems were alive. The dust cap is still on, so it's a fuzzy picture, and that's why it's closed into the circle. That's actually the dust cap. This is one of the cameras on the front of the rover that we use for navigation, for figuring out where to drive. And this is the first uh, terrain picture that we took from the rover once all of the systems were up. And this is actually just a small piece of a giant panorama. One of the first things we do after we boot everything up is look at our feet, because how do you know you landed on the ground without knowing your feet are there? So on the left, you have Viking from the 1970s. That's the Viking landing foot. And on the right, spinning around there, is one of the Perseverance wheels grinding into the regolith on the Martian surface. We also like to take picture from the top deck of our spacecraft. So on the left, you have a picture from a camera that was on top of the Viking spacecraft looking over the Martian terrain. And on the right there, you have a picture. This picture actually isn't from the top deck. This is from the robotic arm, one of the cameras on the core on the robotic arm. But in this picture, you can see the mast looking back and forth between the camera and Ingenuity. So this was shortly after we dropped or deployed Ingenuity onto the ground. You can see the rover tire tracks on either side of Ingenuity. And this was just before we initiated the initial checkouts of Ingenuity to make sure we could fly that helicopter. And again, here's another shot from the top. This is from the top deck of the Perseverance rover. This is the backside of the rover. This is what we call the RTG. It's the radioisotope thermal electric generator. It's essentially our nuclear battery that we have that powers the Perseverance rover. If you've seen The Martian, this is what Matt Damon uses to keep himself warm inside the vehicle he's driving around on the planet. And here's a video of the deployment of Ingenuity. So as you can see, it's strapped into the bottom of the rover. We have a panel that actuates and unlocks and drops down, and the final release releases the helicopter onto the surface, and then we drove the rover away. So this was the very first action that we did to deploy the Ingenuity helicopter onto the surface. One more time there, it's pretty cool. All right. And here's a picture of the Ingenuity helicopter after we put it on the surface. And this was just before we did our initial, you can call them spin checks. We wanted to make sure that we could command the propellers to spin. And here's a video of the propellers spinning. So this was the very first spin test. This was very early in the mission, so the 48th Martian soul of the mission. And a note about that. So when we're operating on another planet, the team of people that we have that are working surface operations adjust their schedules to meet the day and night schedules of the planet that we're on. So in the case of Mars, we have teams that actually operate on the Sol, which is the Martian day. So we have, when we're in the middle of a mission like that, the whole organization of the team is around number of Martian souls of the mission. So I have a few other notes throughout the rest of this presentation about Martian souls. This is the 48th Martian soul of the mission, otherwise known as the 48th Martian day after we landed on the planet. And here's our very successful spin test. We didn't take off when we were doing these spin tests. We were really just making sure that we could rotate the propeller blades. And here's another shot of all of the instruments on the Mars 2020 rover. We have a set of cameras. We call them HAZ cams. Those are hazardous cameras. We use them to identify hazards that we're driving around. We have navigation cams or nav cams that we use to make decisions. When I say we, I actually mean the rover. The rover is using these cameras to make decisions about where to drive. Starting with this rover, JPL engineers are not driving the rover around with joysticks on the ground. We're actually telling the rover, hey, go here. And we're letting the rover make decisions about how to get there. It lets us parallelize a lot of operations so that we don't have to focus on sending commands, specific individual commands to drive around. We're enabling the rover to make its own decisions using information that it receives from the has cams and nav cams and other sensors on the rover body. We also have a super camera that we use to look at the composition of rocks. We have Mastcam Z. The Z is for zoom. On MSL, the Curiosity rover, we had Mastcam, and for this rover, we added a zoom capability. And then we have a couple of cameras out on the core itself. So Sherlock, along with Watson, because you can't have a Sherlock without a Watson, help identify potential science targets, and the Pixel camera helps us confirm the composition of those potential science targets. So I have some pictures from each of those. So there's a picture from the front has cam and the rear has cam. This is just before we touched down on a rock with the core. So we're using this to actually get a cool shot of the core above the ground. And this is where we just drove. So you can see the rover tracks behind the robot. There's a picture of a nav cam. We have what we call a cache cam. This is located on the underside of the rover in our adaptive caching assembly. What that really is a little robotic arm that handles the sample tubes. So these sample tubes, after we collect a sample, we take a picture of the top of the sample. And that's what this is. This is actually a rock inside a sample tube that we took a picture of before we sealed up that sample tube. I have a little bit more about that in a second. And then here's a picture from the helicopter's navigation camera. So that's a shadow on the surface of the Ingenuity helicopter, and a picture looking out on the horizon from the Ingenuity color camera. And here's that mast cam, that camera on the mast of the rover using its zoom capability to look at our bits. So this is the coring bit. You can see a rock inside the sample tube that's inside that coring bit. And this is an abrasion bit. So this abrasion bit cuts a circle on the rock. And I have pictures of what these circles look like. And the Pixel instrument uses those circles to find the rock and then do X-ray lithography, essentially look for the composition of the rock to help us make a decision whether it's a useful science target or not, essentially whether to collect a sample or not. So what are these surface operations? So we've implemented this plan. We collected a set of double samples, and we dropped half of them off on the surface. And we kept the other half on the rover. The reason we did that is in case anything happens to the rover later on in the mission, we know we've at least dropped half of the initial set of samples on the surface that we could send a different mission to go collect. But the baseline plan is to take the samples that we have on the body of the rover, and we've been collecting more samples since then, and that's going to be the set of samples that we bring back to Earth. So this was the idea for the first half of the sample collection campaign. And what do I mean when I say sampling? So we have this core on the robotic arm that's on the front of the rover. That core has two stabilizers. That's what my pinky and index finger are. They press down on the rock to get a stable base, and then we drill into the rock with that coring bit. That coring bit collects a sample, collects a rock, and breaks the rock off. And this is a picture in the top right of that rock. Then we extract the sample tube from the back of the coring bit, and we use the little robotic arm underneath the rover that I mentioned to move the sample tube around. And here's that picture again of the rock inside the sample tube underneath the body of the rover. And this is a seal that we press on top of the sample tube to seal up the sample inside the sample tube for its eventual return trip to Earth. And here's a picture of the first rock that we collect samples from. So here's 2 sample collection sites. You can see this is where we cored into the rock and collected 2 samples with the coring bit. And you can see down here, here's a circle. This is the abrasion site. This is what the circle that we cut for pixel to look for. And I don't know if you see it, but we certainly did on the team. I mean, that's Pikachu, if I've ever seen it. All right. The Ingenuity helicopter, like I mentioned, lasted way longer than we expected it to. We went in planning for a technology demo. We ended up with an operational friend, this tool for us to make decisions about where we're collecting samples, how we're flying forward, how we're going to travel. After its 70-second flight, though, we lost communication during the landing, and we had a pretty hard flight. And so here's a picture of the Ingenuity helicopter's shadow after that 70-second flight in January of last year. And you can see the broken edge of one of the propellers. So we sustained enough damage that after almost 3 years of operation, we ended the Ingenuity helicopter's mission. But that wasn't without a long, much longer than we planned, and very useful mission. So this is a map of all of the trajectories of the Ingenuity helicopter's flights. This is a picture of it landed in this location, but we essentially, because we were sending Ingenuity ahead of the rover, this entire path that the rover ended up taking was carved out by Ingenuity. And I have, so remember this shape of, this is the Jezero crater. We've been collecting samples inside the Jezero crater. The crater rim's over here. This is us getting towards the crater rim and eventually working our way out of Jezero crater. And these are pictures of the first 21 sites that we collected samples from. And this is the same path that Ingenuity took us on. So we were following Ingenuity to collect all of these samples until Sol 72 or Flight 72 that we crashed and lost the helicopter. But it proved, one, we proved that we could do this kind of flying. We could fly on another planet with a drone and use it for scientific operations. We've collected all of these samples that are now riding along on the Perseverance rover's underside. We're collecting more samples, and eventually we'll be able to bring those back to Earth. It took a whole team. So in the top left here is the Ingenuity team. The Ingenuity helicopter team had orange polos, and the rest of the photos are different members of Mars 2020 around the world. So this picture in the middle on the right here, this is in France. One of our instruments was from a French organization, and they joined us during operations and are joining us today still as we continue to collect samples. And so this is a video.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely.
Of our landing. So at the top of the video, you heard Tango Delta. Tango Delta is touchdown. This is everyone around the world watching our landing. You guys saw that image? It really takes a global effort to do something as challenging as sending a rover and a helicopter to another planet. And that's all I had. Like Andre mentioned, I founded Astro Tea Company to raise money for STEAM education. So there's the website in case you're interested in tea. If you want to connect with me on social media, there's my Insta and my Blue Sky accounts. But I'm happy to take any questions you have. And there's me with my cat on Mars.
Thank you so much, Jeffrey, for your presentation.